right. Well, welcome everyone to the EOEPCA workshop. It's my pleasure to give you a very short introduction. I'm Claudio Jacopino, and I work for the European Space Agency. European Space Agency is the one promoting this project. It is an ESA project. And is basically now at the end of his first 5 years funding period. So actually this workshop comes at a nice time when we have reached a few milestones, and we are basically completing this first procurement. So it's my pleasure to basically promote at this stage this project. So EOEPCA stands for Earth Observation Exploitation Platform Common Architecture. It's rather a long acronym, but basically what we've been trying to do was to develop building blocks for an exploitation platform, a generic exploitation platform, and this is what the Common stands for. It's in fact a part of a larger initiative that we refer to the Common Architecture, which target is from one side to provide the common capabilities for anyone working in the field of a cloud-based platform for Earth observation and analysis that could support the development of those platforms. So the idea has always been, if you need a capability that is that could be confined to the point that you could just adopt it, then we offer you a building block for it. So the idea there was one side to support new companies, new business to entering this market that has high barrier in terms of technologies, because we're talking about modern cloud technology. So it's certainly something that is different from what used to be 10 years ago. So one side we wanted to lower those barriers, support a smaller business, and reduce development cost also for programmatic activities inside ESA. The other aim was really to enable federation across the very fragmented landscape we have, at least in Europe, of platforms. Because I guess it's not news to any of you that there are lots of platforms out there, and lots of people don't really know what they are for. And that is an issue that I think is more prevalent in Europe than outside. And so what has been our general strategy has been to support open standards, because the idea there is that we will be able to create some level of federation across these platforms. Clearly, we are not creating a new platform to rule them all. That might be the first thoughts. We rather provide the capabilities to move from one to another in the way that will suit better user and the development of the specific business. Because at the end of the day, we are in a free market, so we need to comply to their dynamics. So that is what has been the general spirit and has been driven the various developments. In terms of standard, we've been partnering with the Open Geospatial Consortium. So for us, they are the authority for the standards. OGC, so what we call just OGC. OGC has been in the years changing towards a more open community-oriented approach, and more and more adopting a standard that have not been created inside OGC. So it's becoming more and more the right partner from this point of view. And therefore, we are promoting this partnership further. So just a few words on what's coming next. So what we'll see today is a detailed discussion on what has been achieved so far. We have released the version 1.3 last month, and 1.4 is just coming up at the end of the year, because in fact the contract is finishing. As I was saying before, we are at the end of this 5 years contract. But a new contract is just started. We probably keep talking about EOEPCA, but will be an evolution of it. There will be a number of changes. There will be a number of new players working on it. And we are moving towards a more open governance paradigm, where we will want more people to directly contribute to the development, the design, and the adoption of those building blocks. So we are going to embrace a full open source approach, and we will do with the help of OSGeo, that is becoming a new partner in this project. Obviously, OGC will play the same role as before, so you will see a continuity from a number of points of view, but you will see also some news. So without any other words, I'll pass it to Richard, that is the technical lead of the project, the past and the future one. So there is continuity there as well. Thank you very much.
Okay, so the tutorial is designed really as a hands-on. So we have some Jupyter notebooks prepared, which I offered. Hopefully you looked at the information that was circulated. There are various approaches to running it. So the one we have here is probably the easiest. Is if you have a GitHub account, you can go to our repo and run it from a GitHub code space. There are other options that were also presented for running it yourself in Docker or indeed in a local Python. So if you're using the code space, you'll end up with an environment a bit like this. And the only thing you have to do, oh, sorry, strange keyboard. There's a script. That's the one. And that will run the Jupyter environment inside the code space, and it will use a bit of port forwarding to give you access to it. There we go. So this should take you into a Jupyter Lab environment where we have a set of notebooks. Claudio's done a brilliant job of covering most of the introduction. Thank you, Claudio. So here's the agenda. So quick introduction, and then we're going to go through not all of the building blocks that Claudio mentioned, some of them particularly focusing around discovery and search of resources, services for data access and visualization, linking that into a user workspace concept, and then finally processing. So we have various, the way the project was set up, so Telespiazio were leading at a system level, but we have partners. We have Angelos from EOFarm, we have Fabian here from EOX, and Fabrice from TerraDue, and Gerald from GeoLabs. So all contributing to the overall product. So I'm going to skip, you have access to these sheets. Right, sorry, just getting the hang of the scrolling on this. I don't want to go over everything that Claudio said, but fundamentally we have a set of building blocks. We've defined an architecture to encourage interoperability using open standard interfaces, focusing a lot around OGC standards. We've developed a set of building blocks, which is mostly highlighted here. I guess the focus of this is the bottom two layers here around the sort of the access to resources and the processing. The problem we're solving, interoperability through standards. And this sort of represents the reference implementation, a bit of a simplification, but fundamentally working from the bottom upwards, the idea is that the exploitation platform sits on some infrastructure with some data. You can harvest that data into the resource management services. You can develop application packages. So we do have a building block, the application hub we call it, which helps you develop those. We're not demoing that here now, but Fabrice is doing a session afterwards, which is very much focusing on that topic. So you can perform processing in the platform to create added value products, which you can then register in your workspace, and then again through the application hub present dashboards. So I'm conscious of time. So I guess the key thing at this point, because I'm going to hand over to Angelos, who's going to start us off with the resource catalogue aspects. So I'm assuming everyone at this point is able to follow through if they want to in their local notebooks. Please shout if you've got an issue there. So Angelos, is joining us on Google Meet because his flight was cancelled yesterday. He is arriving tomorrow, we hope. Can you quickly speak, Angelos, just to make sure we can hear you?
Yeah, can you hear me?
Perfect. Okay, so if I put you on full screen, where's the full screen button?
Top left.
Top left. This one here?
The green one, yeah.
Ooh.
No, further top. Yeah.
Ah, okay. You can tell I don't use a Mac, can't you? Okay. Perfect. All yours, Angelos.
Great. Can you see my screen?
We can, yes. We can also see our pictures as well. I don't know if that's good or bad.
Click on the screen.
Is this okay now?
Is there a focused view? Is there a French? Not good with that either.
Sorry for all the trouble. I should be there. Yeah.
What you want?
I guess just to focus it on the screen share. Perfect. Okay, thanks. Okay, all yours, Angelos.
All right. Thank you. So yeah, we have prepared a notebook for the resource catalog. So this part of the workshop we will discuss the EOEPCA resource catalog building block. The resource catalog is built upon the OSGeo project PyCSW, and PyCSW is an OGC API records and OGC CSW server implementation in Python. We support all the latest standards from OGC. We support CSW2, CSW3. We support the OGC OpenSearch Geo and Time extension. And of course, we are also supporting the OGC API records, which is now in development, and we know it will be released until the end of the year as a standard. Of course, during the project, we have worked to support also the Stack API, which is now a community standard in OGC. So this notebook has some examples on how to do data discovery, search, and transactions using PyCSW. By the way, if you are a PyCSW user, you will realize that there have been a lot of changes in the user interface because we are now working on the upcoming version of 3.0 of PyCSW, which is not yet released as a final release. We are hoping that we also do that by the end of the year. So here in this notebook, first of all, before going to the notebook, I will just show you how it looks like on the browser. This is the landing page. All these links are also in the notebook. This is the landing page of the catalog. Here you can see that there are links. This is the new OGC API records landing page, which is in HTML rendering. There's also the option here to do this in JSON format, exactly as you would expect from any OGC API endpoint. Okay, now it takes a bit of time. I don't know why. Yes, this is it. So this is the JSON representation of the server now. And here you can see, for example, we have the collections with several data, and there we have items within collections. And of course, this includes a map and several items in the map. So at any point you can render, you can drive through the HTML representation, but also switch at any point to the JSON representation. So the OGC API records standard supports, doesn't mandate any specific output, but it is recommending HTML and JSON as the main blocks for the standard. So this is how it looks like on the browser. And going back now to the notebook. So we are going to use this server. This is the demo catalog of EOEPCA. So in EOEPCA, what we do is that we have a building block that you can build a central catalog. Of course, you can federate other catalogs within PyCSW, and this is currently supported by the CSW standard. But also, you can always deploy a catalog within your workspace. And Fabian is going to talk about workspace a bit later, so I'm not going to go into more details about that. Here for the notebook, we have this will be demonstrated using the OWS lib library. This is a Pythonic library, which supports many open OGC web services. So it's a client library, and in this case, we are using the CSW client, the OGC API records client, the open source client. We have the filter and coding standard for several filters that we are going to build during this demo, and several other libraries. So without any more delays, we are loading those libraries from the notebook. We are defining the domain that we are going to work on, and then we provide the system catalog endpoint. So the first part of the demo now is to work and discover data with the OGC CSW standard, because it's like the oldest here and the most well-defined. So we will start with that. In the new PyCSW implementation, all the standards have a subpath. So you go to /CSW, and then you have the CSW. Or if you go to /stack, you will go to stack, and so forth. So I'm now defining the CSW endpoint, and I'm loading the OWS lib client for this catalog. And then we have a CSW object where we can, of course, query for metadata. For example, the identification type, what's the version of the CSW that we are currently working with, the operations that are currently supported by the CSW server, and of course we have some catalog queryable that we can use. So here is a list of the queryable that are available in the catalog, and these are all defined by the API application profile of the CSW. So you will find here, for example, the name of the server. You will find dates. You will find description, keywords, and so on. Abstract and many other queryable that are defined in the core of the model. All right, and now I will do a generic get records request, which will give us all the results that exist in the catalog. So we have preloaded the catalog with almost 50,000 records. These are all being paged by the server, so the server will return them in of course, pages of 10 records. And for example, here we can print easily the identifier, the title, and the type of the data set for the first 10 records. So this gives us some Sentinel-2 scenes that are already in the catalog. The next step is to perform a filter, to perform a search, a discovery. So this can be done with various queryable, and of course, the most common ones are bounding box, time, temporal searches, and attribute searches. So in this example, we define a bounding box, and then we are defining a greater than or equal to property search for the time extension. So the temporal extension should start from 10th of September 2019, and the end of the time of the temporal extent will be the 2 days, so the 12th of September. And we also define that we want a cloud cover less than 20%. And then we create an OGC filter, which is this is the syntax of it. We define a list of filters and we merge them with an AND operator. So this is how to construct the filter in OGC CSW, and then we provide the filter list as a constraint in the get records request. So we are filtered down to 2 matches. So we found just 2 scenes that are in this bounding box in this specific time and have this cloud cover. And it's very easy now to just select a record based on these returned matches and then print some metadata out of those records. Another option is to do a collection search. And in order to do a collection search, we just need to define the parent identifier, which is the identifier of the collection where the data are listed as childs. So in this case, if we want to do a Sentinel-2 level 1C search, we define the property of parent identifier to that name of the collection, and then we can see that for that specific collection, we have 24,000 records that exist in the catalog. And of course, then we can do a constrained search on top of it, and then we can see how many exist in that specific bounding box. Of course, we can always perform several different, we can perform any kind of search we want in this way. So for example, we can do a bounding box and an any text search. So we are using a bounding box and then the orthoimagery keyword to do a search throughout the catalog. And this is all optimized in the server side because we are using Postgres as a backend, and we get these all are translated to SQL in Postgres. That's how search is working in CSW using the OWS lib. And this is a very small snippet when somebody can actually parse all the records by 10 by working on the start position of the paging of the server. So for example, if you want to list more than 10 records, this is how to do it. This is just a small example of how to do it. Then we can, just by selecting the record that I kept the ID of one record before in a variable called selected record, and here you can see that we can actually parse that record directly from OWS lib, and this is the full XML of that record in ISO 19115. Sorry, the rendering here is not very well in the notebook, but we can see other examples later. And after we have selected the record, we can browse through the links that are available. And in this case, you see there are links pointing to the Sentinel-2 repository in CryoDS, where these data have been harvested from. So we can see all the specific items, the specific assets of that record being listed here as links. And you will notice also that the two last links have to do with the data access that Fabian is going to demonstrate a bit later. And those are a WMS endpoint and a WCS endpoint that has been offered by the view server of EOX in this case, and will be demonstrated a bit later. There is the capability also using the GeoLinks Python library to parse through the links and also identify what kind of links they are. And in this case here, we are looking for WMS links and can be done with this single block of commands, or the WCS links are available here. And of course, we can use the volume map, for example, like a very small snippet to present the bounding box of the record that we have discovered on a map directly on a notebook. Okay, so we demonstrated how to do this with CSW. I have a list of other standards that we can use, but we don't have enough time for all of them. There are examples here how to do the data discovery with OpenSearch, for example, and this is how we are using the OpenSearch client that exists in OWS lib. So I'm going to skip that part because this is mostly the same. I'm using the same filters to do this with OpenSearch and get some results. And we also have the OGC API records client, and this is also done with OWS lib library. And this is how to list the conformance classes of OGC API records. You will also identify here that we also support Stack API within the same server. So this server is both compliant to all OGC API records and Stacked API at the same time. This is the API, the Open API document for this server. You see that this is the Open API document here listed. Sorry, too much here. And of course, we can list collections in a JSON format and also search how many records we have. And this is actually the collection number. And then we select the collection and we do a collection search by defining a specific collection. And of course, we can always get the total number of records, and also we can get in a Pythonic way by just browsing the object that we get from OWS lib. We can parse the properties that are exist in an OGC API record document, which is a plain GeoJSON file. Then this is a query using filters, again, by a bounding box, same result number. And also we support now the CQL query language. It can be done either by text, using the old text SQL language. For example, this is a filter that says title has to be like this string here, or we can do this by the SQL, the new JSON SQL query, which is called SQL2. So we can define an operator and some arguments in the SQL, and this is like an example how to match a specific identifier. And by doing this, we get also the same result here. So the next part, and I know that we are not running out of time, we have the same similar functionality using a third-party client library, which is the PyStack client. And this is a library, a Python library that the PyStack community works with. So we have tested the PyStack client against PyCSW endpoint, and we can do stuff like identifying the catalog, search the catalog, browse through the conformance classes of the catalog using the Stack API, and of course doing direct validation of the catalog. So you see here that we have no problems. It validates perfectly with what it is there in the Stack, in the PyStack client. By the way, in the most recent version of PyCSW, there's also a better Stack implementation, which also now works perfectly with the Stack browser. So if you are on Stack browser, you can directly point to PyCSW and then browse through a collection. And this is all now supported, and you can see in PyStack, sorry, in the Stack browser, you can see what is expected from the Stack API that we have implemented. And here you see that the search also is supported. So for example, we want to do a collection search on Sentinel-1 data and do a submit, and we get the records that exist for this filter. Okay, going back to the browser. I'm going to skip the rest of the Stack demo. And now for transactions, there are two things that we support. First of all, we support, we have in EOEPCA, we have a module that is called the registrar. And the registrar is a module that is waiting. There is a queue, and we point records to that queue, and then they are being harvested. And the reason we do that is we have not only PyCSW in the Stack, but also we have the data access layer with the view server of EOX. So in this case, we need, whenever we register stuff, we want to make sure that we register both to the catalog and also to the data access. And this registration API exists, is part of the Kubernetes setup, and there is an endpoint where we can register stuff. So in this case, we can use a generic Python library like requests, and then we are going to do a registration. We are defining a registration endpoint, and then we are sending a request to register something. In this case, we are registering an OGC API process endpoint to the catalog, and then after a couple of seconds, we test that catalog to see if this service is there. So yes, it has been registered, and this is the JSON object which points to a processes API, OGC API process API, and all the links that are along with it. And of course, we can use the registration API also to register a Stack item. So I'm using an upstream Stack item here from the Stack specification. I'm downloading it, I'm sending it to the catalog, and then I'm doing the same for an OGC API records catalog. And then we can see if we have those items registered. So yes, we have the Stack item that I just registered in the catalog is named simple collection here. sorry, this is the collection of the stack item, and the stack item has this identifier here. And this is how to do a transaction through the EOEPCA architecture. So I don't have enough time. I think I'm close to 15 minutes or even over it. So what I'm going to show you now as a last example is how to do a search using QGIS instead. So I'm now going to share full screen here. Share. You should be able to see my QGIS now. Is it okay? Can you see? Yes. Okay. So now.
Yes, it's through now. Yeah.
All right. So what I'm going to do is I'm going to zoom into a place here, for example, and then I'm going to use the meta search, which is the default catalog client in QGIS. So I have the EOEPCA demo client server here defined, and we see the service information. This all works within QGIS. And then from the search button, we take the map extent, and we can do a search. So here you see several records coming up, and you can browse through the records, and always, for example, okay, this is the record I want to see, and then if I double click, I see the record metadata as it has been discovered by QGIS client, which is also using the OWS clip client underneath. We can see a full XML for that record here with the links. And we can always click the add data. So for example, I can add the WMS for this record directly. It will show me what is there in the view server, and then I can click on the NDVI and add it to the map directly. And it should be a couple of seconds before it gets here. It should work. I did not press it.
Oh, you've got a warning there.
Yeah, maybe timed out. Yeah. Anyway, I just got the outline, and you'll see the demo of WMS in a few minutes from Fabian. So, yeah, that's my part. Sorry if I took longer than 10 minutes, but lots to cover. So if you have any questions, maybe at the end of the session.
Thanks, Angelos. Yeah, we only have an hour and a half. We're trying to cram quite a lot in, possibly too much. So the next topic, two topics actually, Fabian's will do data access and workspace. Regarding the workspace, a workspace is a sort of a resource in its own right, either a user or a project or a group. So in the interest of time, we've pre-created some workspaces. There is an API through which you can create workspaces. I've got a sheet here. I'm going to hand it around, a few copies, so you can look up your workspace name, so that if you want to follow along, then you can interact with your own workspace. So I'll hand those out.
All right. Data discovery just covered. Now data access. Okay, so the workspaces will be the second topic I will be talking about. For the first topic, you can still listen in. EOEPCA components, the resource management component of EOEPCA consists basically of the two parts of the resource catalog of the one hand side and on the data access on the other hand. The resource catalog we have just seen, and for data access I will be exploring it a bit. What does data access actually mean? We want to access the raw satellite data. We also want to access rendered data, pre-rendered data, in order to give them put them on some map interfaces. This is the first part of this notebook is rather dry. So there's just some imports we will be using later. So this This will explore the data access from the Python side, but I think it should be also interactive in a sense. So just some imports in the start. Here we have the base domain, which is dataaccess.demo.eepca.org. And then we have /OWS, which is the endpoint for all the OWS, so like WMS, WCS interfaces. We connect to that. There will be some warnings, but these are inconsequential. Here we can list all the layers that are available. So this is very similar to what we have already seen from Angelos. And here you can see a couple of satellite missions and data products. So for example, we have a couple of Landsat ones, and we also have Sentinel-2, various levels and various products. And you can also see that there are some sub-layers. We cannot see the hierarchy here, but in the WMS capabilities, they're actually structured in a tree-like structure. So we have the root layer, Landsat 8, L1, GT, and then we have the sub-layers outlines, outlined, true color, and so on. Outlines is, as what Angelo has shown, is just the outlines, just the footprints of the scenes rendered into a map. But there are maybe others as well. So for example, the true color one is a true color composite of the image. How this is mapped, so there's extensive configuration how this is mapped internally, so this is not part of this presentation. Just to know that this is very extensive, there's a very extensive configuration efforts behind that. So for true color, for example, we don't use the provided RGB images, but we actually make our own color composites. For the purpose of this demonstration, I will be using Sentinel-2 Level 1C, so this is what I have selected here. We can already see like what is the global bounding box of this layer. So we only selected a subset of the available data sets just to give you a little bit of boundaries on what can be explored. So here we also define a, this one. It is just a helper function. The getMap function is basically just a helper function in order to bring something on the screen. Okay, data access. For us, it means various steps. For one is to actually browse the data. Browsing means not only looking through XML to actually find the ones that you're interested in, but visual browsing. And visual browsing, for example, here we simply select the S2 L1C outlines bounding box. And you can see that this is a mess of hundreds of thousands of products rendered into a single image, which is, I mean, it's cool that it works, but it's not really useful. But we can actually, in the WMS request, when we specify the time of interest, we can drill that down, and we can get a much more cleaner image now. So now we have, I think, 1 day selected. Yeah, this is one single day of acquisitions, which is good. But we also can we can also provide a SQL query to select on the product metadata, for example, to only select scenes which have a cloud cover of less than 10. And we can see already that many scenes have been filtered out. These functionalities are not just for the outlines layer. Of course, they're also available for all the other layer types like RGB rendering. But in order to not kill our services, because this is not cached here, I'm not accessing the cached version of these images. I'm directly going to the data access. So it will actually produce a rendered image all the time. This is better for testing and better for demonstration purposes. Okay, now I'm going to visualize a couple of scenes. Here I pre-selected a Sentinel-2 scene. So this is the scene identifier, and here I will create a SQL query. And when I pass the SQL query to the OWS endpoint, we actually get a capabilities document only for that particular scene. So this is useful because in the default case, we don't want to overwhelm any client with like a capabilities document that is gigabytes in size. So there we only show the root level products like Sentinel-2 Level 1C. But here we are actually using a SQL query to give us the capabilities of a single product. This is useful to then, for example, put it on QGIS because you then have a URL to that exact product. And we can see that we have, again, the structure of layers. Sorry. So this is the base layer. Then we have the outlines, outlined, false color, NDVI, and true color. And we're going to click through them. So here is the scene bounding box. We get it from OWSLib again. And here we are actually rendering. I don't know. Angelos already experienced it. It was quite slow today. I'm not sure. Maybe some people are already accessing it. So it might take some seconds. So this is the predefined TCI image. It's called. In Sentinel-2 scenes, we get a preview image which is called TCI, standing for True Color Image, which is great for exploration, and we can put this on a map. But we actually can also provide our own. So here we are using the True Color postfix, which is then making a custom rendering of the actual data bands beneath. So this is using band 4, 3, and 2 of the Sentinel-2 scene, and we make our color composite on our own. Here we already have predefined some color stretches, so how each individual band is stretched, because each band has it is not RGB, it is not each pixel is not bite-sized. It's actually UN16, so we have to scale it. But this gives us much more flexibility on how to scale it. And here we are using a custom stretch of the values, so we get a little bit lighter image, which is already more beautiful, I think, than the TCI one. Okay, next thing is we can also make another composite, which is the false color composite. I think I just restarted the True Color one, sorry. I have to wait for that again. Yeah, while testing it, it was way faster, but of course, if many people are now accessing it, then it's not as fast as I hoped. So for false color composite, usually the near infrared band is used as the red color. The red color is used in the green channel, and green colors. Sorry. Yeah. Okay. Sorry. So band 8 is red color. Band 4 is the green color composite, and band 3 is the blue color composite. And we can see that it's almost producing some reddish schemed things. This is always useful to look at a vegetation, for example. This is also why it is used in the NDVI. NDVI stands for normalized, digitized? No, difference, thanks, difference vegetation index. And it's actually using the infrared and the red band to calculate it. And what we can see here is that we have it somewhat styled. Let's start the next one as well.
These are effectively calculated on the fly.
Yes, exactly.
The definitions that exist on the back end.
Yeah, this is true. So unfortunately, we're running into timeouts here. Yes, it is. This is on the server. It is actually taking the specified bands, makes the calculation, and passes through a rendering process. By default, it's using just a black to white color map, but we can also use, for example, the very famous BiDS' color scaling. If I can show it. Sure.
So we could have scaled up the number of renderers.
Yeah. We already did upscale the number of renderers, but unfortunately it was not enough. Seems like it. So we are running into timeouts. This is very unfortunate. Let's try again. No, I'm very sorry. Okay, well, continue. Maybe the others will work. So, for example, we can also make our custom color composite directly defined by the user. Here we specify the WMS base layer, and here with the dim bands, we select the bands that we want to make our RG and B components. When we run this, and let's hope it works now, we also have the dim range here. And dim range basically allows us for each color component to define our custom stretch. So we map all the values from 0 to 4000 to the visible spectrum. And here it works now, finally. So here we basically, we have the SWIR rendering. So we select band 12, 8, and 4 and make our own color composite, and we make the default stretch. You can play around, not too much, because I'm still demonstrating. I hope it will not kill my presentation. But you should be able to see different results if you select different bands or different stretches. And of course, it's all nice and dandy, but we can also put it on our maps that we have already seen from Angelos. He already used it. Here we have the same scene over Greece, and we should get a nice rendering of that in just a second. So this is an interactive map. Currently, I agree it's not too interactive because of bandwidth. Okay. I think I will continue now. What if we actually want to use the real raster values instead, not just the pre-rendered version? Because, for example, we have some algorithm which requires the usage of the actual raster values. For that, WCS is perfect. In WCS, you basically define the data access service actually provides the EO extensions for WCS, which gives us the special describe your coverage set command. With that, we can explore a single product and see what is actually inside. So here we see for this one scene, we see that each of the bands is in its own coverage. And when we now say, so this is just a helper function to visualize a coverage. And here I'm making the get coverage request, which extracts the actual raster bytes for the 4th and the 8th band. And if you see 4th and 8th bands, you already know that we're going to calculate the NDVI. So we get both of those, and let's hope we don't run into timeouts here. Yes, we got the data, and we can now calculate the NDVI now on our home turf, on our own machine. These are just NumPy arrays. I'm reading them using a TIFF reader library, extracting the values, and simply making the calculation on my own. This is just for demonstration that you can actually access the raw raster values as well. Right, so let's see if we can see some nice images over Greece. And if you look closely, you might spot Angelos still sitting in Athens. All right, yeah, maybe, yeah, we just continue with the user workspaces now. Has everyone who wants to participate on their own got his own workshop, workspace number? Okay, all good. Then we'll start with that. Okay, so this is the user workspace. User workspace is, as Richard.
Quickly, we're running quite short of time.
Yeah.
So if we can accelerate through the workspace, we'll leave time then.
Yes. Okay. Okay. It is not just important that you override this value here in user 99 to the number of your workspace that you have received. I will speed through that. A workspace is basically an own set of APIs that only you have access to. With this demonstration, we removed all the access restrictions in production setups, there will be access restrictions that you need to handle with your access tokens. But here it's not. We can actually get the workspace details. Workspace details is important because each workspace has its own S3 bucket, which we can interact with. And these are the workspace details for our demonstration purposes. So we get our access and secrets for our bucket, and then we also have the endpoint of the bucket. I prepared a scene. Okay, so this is the application package that we will upload and which we will later execute. So this will be part of the last part of the demonstration. Here we simply demonstrate that we can upload it and then register it. And we should be able to see it now in the. So we have now uploaded the application package for later use. But we can also upload, so this is also what the ARDIS is doing. It will upload and register all its processing results, and we're simulating that now. This huge code block takes some data that we already prepared here. So there's a data directory, there's a processing result directory, which is basically a stack collection structure. We will fix up the links because the links need to be absolute links, so it needs to include the workspace URL. So we need to fix up the links inside, which is quite fast. And then we'll be uploading the whole package to the S3. This will take a couple of seconds because even the scaled down image is still 75 megabytes in size. So it is already concluded. So then we can list the buckets. I'm actually on a testing setup here. I have a couple of more files than you have because we tried around a bit, but you should get at least some list of files that were uploaded. Then we register it. Register means we point to the stack catalog of the processing result and ingest it into the workspace catalogs. So this worked. And now I'm defining a couple of helpers to get the map and to get the coverage, and then we can actually explore it using the data access system. Here we're again using getMap to make a visualized result of the NDVI calculation of this particular scene, which is working, and also for using getCoverage to access the raw data, not the pre-rendered data, if we want to use it for any other purposes then again, and just plotting it using Matplotlib. Then each workspace also has its own catalog. Just for demonstration purposes, we are now accessing the catalog of this particular workspace, and we should only see the results that were registered into this particular workspace catalog. In my case, it's 4 because I haven't cleaned it up, but you should see exactly the one scene that you have registered before. And you see the record and you see all the links. All right, that was very fast. Play around a bit if you want to, and I say thanks and give over the microphone to the processing team.
Yeah, so I realise we're going quite quickly through this. What I would say is the system we're using, our demo cluster, will remain running in this state for some time, during the week. So you can go work on these offline if you like, and they should still work. And then if you've got any further questions, you can come and find us.
So, hello, my name is Fabrice. I am going to show you the concept of the application package in the EOEPCA and also in the Open Geospatial Consortium where this was born. So actually this is the same deck of slides that we will see in the... Yeah. I'm in the Google Meet. And
oh, I'm not showing you. You just need to select the Google Meet. It's just a tab in the middle there with a red dot.
Okay. So I'm happy that you see what I see. Okay. So this is a very light introduction to the context of the application package implemented with the common workflow language. We will have Gerald from GeoLabs showing the implementation that we have on EOEPCA we're transforming an application package into a web service behind the OGC API process API. Okay. So and now let me get back to this. Okay. So we at the time identified a few drivers for implementing the approach behind the application app package. So the first thing is we wanted to decouple the application developers from the exploitation platforms and between the operators and the consumers, because in the end an application package should work in different environments than a platform. You don't develop code for a platform. So if your code starts with import some library from a platform, then there's something wrong because you have a vendor lock-in, a library lock-in, or whatever you want to call it. So in the end, our driver in the end, it was to focus the application development by minimizing the platform particularities and making those application packages in the end compatible with several execution scenarios. So the strategy here, if it works on your computer, it should also work on the Kubernetes, on HPC, or behind an OGC API process endpoint if you have deployed it. So those were the drivers at the time. So it's actually the result of a long thread of OGC testbeds and discussions between testbed 13 and 16. So during testbed 13, this is where the concept of the application package was born. So in the end, it was a wrapper around a piece of code that you would deploy on a WPS endpoint. And so, yes, that was fine at the time, but we end up reshuffling a bit the objectives and saying, okay, can the common workflow language actually convey all the information for us to deploy an application on such an endpoint and see what are the other benefits. And so this is why we wrote the OGC document 2089 for the best practice to package and deploy your observation applications in an exploitation platform. So it defines guidance for 3 viewpoints: developer to adapt an EO application. So in the end, if you have a series of command line tools that you want to wrap as an application package, this is where you start from. An integrator to package that application package, so getting all the envelope around it, and for a platform to deploy and execute the EO application. So we were quite a number of organizations submitting this best practice. You have the European Space Agency, the Canadian Centre for Informatics, Telespazio, Solenix, and so on and so forth. So in the end, we mentioned command line tools. Well, those are included in containers. So this is nothing related to Earth observation domain or context, but containers are definitely a very nice way of packaging your software libraries and making sure that if your container works, it will work somewhere else as well. So the container will carry on the runtime environments, dependencies, and application binaries. But then an application, an Earth observation application can have different steps, steps that could fan in, fan out, and invoke different tools in containers. And so this is why we also have the capacity of orchestrating that with the common workflow language. So actually, the common, are you familiar with the common workflow language, or is it the first time that you have, you hear this, well, not you, Fabian, but the others? It is an open standard, so used to describe analysis workflows and tools in a way that it makes them portable and scalable across a variety of software and hardware environments, from workstations to cluster, cloud, and high-performance computing. This is what the definition that you find. And the fact is, it doesn't want to bind you to something. It will orchestrate the command line tools via the specification for command line tools, and it will orchestrate those command line tools with the workflow specification part of the CWL. This is actually what we have said. Maybe in Earth observation, it wasn't a workflow specification so known. In the last 3-4 years, we have made this effort to bring it in the context of Earth observation, but it is very well known in bioinformatics, medical imaging, astronomy, physics, and chemistry, for instance. So what do we have? So application developers create containers with their runtime environment dependencies, and this describes the inputs and outputs, service parameters, service definition with simple things as ID, doc, and label, and you can map that to title and abstract in the OGC thing. So this is an example of a workflow that will have a few inputs, pre-event, post-event, bounding box, projection, and will generate an output. And then, it does a very simple approach also to run inline code in a container as well. So different approaches to run. The workflow will orchestrate command line tool steps, and the command line tool is a very simple abstraction to create the command line that your tool needs in the container. So it will map everything that you need there. So then you can orchestrate that as a computational workflow. Each step invokes a command line tool in a container. Steps can be parallelized to speed up the execution. For instance, in HPC and Kubernetes environments, this is quite useful. Also on your local computer, if you have CPU and RAM, you can run the containers in parallel. That is fine. So in terms of data management, there was a really big gray area here. So we've all gone through the experience of calling our file names NDVI over the best area of interest using the best algorithm we like, .tiff. Well, was definitely a very weak approach for making sure that your application become portable in different contexts. And so we believe that the stack specification definitely covers the gap here, because it abstracts the application from having to doing glob or find on your file system, or to understand where the S3 enclosure or HTTP enclosure for a TIFF file, now that we live in a cloud native processing environment, is. So stack definitely brings that. So the stack is used as the input manifest when you have to deal with geospatial data. And then, of course, when you produce a result, you also encapsulate that into a stack catalog so that your single GOT file not becomes an asset in an item or several items. And you can put a lot of properties. And you can also, if you find that the stack extensions do not cover your use cases, propose extensions that will get additional information around your results, for instance. Then, okay, in terms of data management, we have established that the staging is the task that will get a remote product locally for processing and will generate a stack catalog. And the input type in your workflow will be a directory. And this is how you tell the platform that you have to have data staged, because staging and stage out is different, typically operations that platforms do, each one in their own way. So you have to use S3 credentials, you have to use whatever credentials, FTP or whatever. This is what we define. So staging and stage out typically are outside the boundaries of an application package. So, and when we execute that, of course, in the platform, in this case, the execution scenario is a platform, the platform will plug its own implementation of the staging step and stage out step. And the outcome is a larger CWO flow that will take the application parameters, but it will also take the additional staging stage out parameters so that your inputs are available to the application, the outputs are available, the output parameters are available to the stage out. So this is a summary. The application package role is to describe the data processing application by providing information about parameters, software item, executable dependencies, and metadata. Ensure that it's fully portable. So a CWL will run on my machine, will run on your machine, as long as you have a CWL runner and you have potentially a container engine, could be Docker, Podman, or anything else. And it contains also the information model to allow its deployment as an application as a web service on a GOC API process compliant web service. Okay, so an example, a list of suggested execution scenarios: a local, so you download the CWL tool and you install Docker or Podman, and you're up to go to run application package on your own local computer. For Kubernetes, you have the Calrissian CWL runner, and instead of triggering a container like Podman or Docker would do, it creates a pod on Kubernetes. So you see the scalability at that stage is very high. On HPC, you have the toil CWL run implementation, and then it will use the Singularity container format. And then as an OGC API process, EOEPCA brings strong contributions to the Zoo project, where the Zoo project's DRU is the implementation of this concept of deploying an application package as a web service. And that I will leave the floor to Gerald, and that he will show you how to do that with Zoo.
Hi everyone, so I will be the last to discuss and to present you the OGC application, the OGC API processes implementation based on the Zoo project that you should be able to access using this URL. So if you go back in the notebook and you go in the processing notebook, you should have a link at the end, processing notebook. So here you have the link to the OpenAPI page. So actually, rather than providing you a Jupyter notebook, we decided to try to embed everything within the OpenAPI which is exposed by the Zoo project. So at the beginning, the building blocks of EOEPCA was named ADES for Application Deployment and Execution Service, as presented earlier. It's a building block of the EOEPCA platform, and we have integrated the work made in ADES directly within the Zoo project open source project. And we have named it the Zoo project DRU. DRU does not come from nowhere. It comes from deploy, replace, and undeploy, which is the current draft specification the OGC SWIG is working on, which is named OGC API Processes Part 2, Deploy, Replace, and Undeploy. So the idea was to be able to use this draft specification and potentially adapt it for being able to deploy automatically the CWL application encoded as Fabrice presented to you, introduced it to you, directly within to be able to interact with using the OGC API Processes Part 1 core. I don't know if you are already familiar with OGC API Processes Part 1 core, but basically it permits to discover and execute processes that are made available on the server side. So you can have a server implementation which may have 700 processes available. And then you can interact with, meaning that you can feed inputs to the processes, execute the processes, and get back the result of your processing. So if you take a look at the OpenAPI, which is trying to also summarize what is available in the current OGC API specification, so we actually started by quickly present the OGC API common part 1 core, which is basically defining what is a standard OpenAPI OGC API is able to provide. So you have 5 important conformance classes, which is the core conformance class, landing page, OAS30, HTML, and JSON. Then you have the OGC API processes, which is built on top of this, where we add multiple conformance classes. I mean, I try to also present the way that EOEPCA is based on building blocks, and nowadays OGC API are also based on building blocks. So you have the OGC API commands, which is a building blocks, the OGC API processes part 1 core, which is another building blocks, and you can add another building block, which is named OGC API processes part 2, deploy, replace, and deploy, which is currently only a draft specification. All these draft specifications are available online. You have the links to each of them, so you can consult them afterward. So let's try, first of all, obviously, as we are speaking, just quickly, as we are speaking about deploying new application on a platform, we are obviously requiring to authenticate our user. This is why we are using a key clock server to authenticate your user. I guess you have the password to authenticate? You gave them?
Password is on the sheet, actually.
Okay.
I didn't mention that earlier on the sheet with the password.
And you have the instruction included within the OpenAPI to show you how to connect your user. Actually, it's very simple. Not all the endpoints are secured, only the ones that are need to be. So what you can do is simply clicking on this lock, small lock on the right here. You can enter the client ID, which is provided within the documentation, within the OpenAPI introduction. And here you can use your user login. So I will use this one, which is an alternative one. And once you get connected, you should be able to interact with the service in a proper way. Okay, so here I have an answer, and obviously if I disconnect, I will have a 403 response. So anyway, if we go back to the initial purpose of this presentation, I want to still introduce you the basic of the OGC API common core. So in every OGC API, you will always have a landing page, which is accessible through the root. So it should contain all the links to the underneath endpoints. So actually here you can add also, furthermore, meaning if your server implementation was able to implement other things that OGC API processes, you may add more links here. Then you have the conformance class. The conformance class is very important from a client application point of view, because it defines what are the capabilities of the server implementation, meaning what the server implementation is conform with. So here you have the list of the conformance classes that are currently supported by the Zoo project DRU. So as you can see from the first in the array, the first items in the array, you can see the OGC API processes part 1 core conformance classes that are followed by 3 conformance classes about the OGC API processes part 2 draft specification, which defines 3 conformance classes: the deploy, replace, and undeploy, which let you define whatever is the encoding of your processes to deploy, replace, or undeploy your processes. Then we are defining the OGC API draft part 2 draft specification defines then 2 other conformance classes which are only targeting encoding, meaning that it will let you know how you can encode your application to deploy it as a process on the OGC API processes. Then you have the OpenAPI endpoint, which is actually nothing to be shown because it is the OpenAPI which has been used to build up this user interface using the Swagger UI user interface. So here you can access the list of the processes using the processes endpoint. So you can click on the execute and you will see the default processes, the processes that you cannot use with OGC API processes part 2 draft specification, meaning they are the default processes that are available per default on the server side. One may notice that we have a mutable attribute which take the false value, meaning that you can only interact with these services using the OGC API processes part 1 core. Also, you can see in the job control option the way you can execute your process. Are you able to run it synchronously? If you have the sync execute item in the job control option array, then it means that you can. Then it is the same thing for asynchronous execution and dismiss. Maybe you may think at this point that it is of nonsense to discuss of this, but afterward you will see when you will deploy your first processes that it makes actually a lot of sense. So as I was telling you earlier, you have multiple encoding supported for deploying an application package. The first one is CWL, and the second one is actually what we call the OGC application package, but which rely also on the CWL encoding, at least in this implementation, meaning that you, rather than providing the CWL file itself, what you can do is provide a link to this, a link to this same CWL file and encode it as a JSON object. So for the purpose of this demonstration, we will only use the CWL encoding. As you have noticed, when I switch from one encoding to another, you may have the necessity to click on the reset button to make sure the file is properly shown. So once you click on the execute, what happened behind the scene is that your CWL application will be, oh, interesting. 509 mean, okay, no issue. It simply means that I already have one application with the same name which is deployed, so I can hopefully deploy it using the deploy endpoint. Oh, and here I have a segmentation violation. Okay, not that good. So maybe I will log in with another user then. Sorry for this. Up. Oh, I cannot actually connect with another user. So anyway, maybe you can try this yourself, and you should get at the end of this execution actually a proper process summary from here. I'm not sure if I will be able to solve this. Water bodies. Oh, let me check something. Okay. So this is my fault and not the fault of the software, because I have a typo in the CWL. You may have noticed that I said, oh, okay, actually I can also solve the issue in the W, because you see there is a workflow identifier which you can set as a parameter, and you may have noticed that it is pointing to the entry point of the CWL file. So the entry point is here, and as you may have noticed at the beginning it was the underscore. When I use the workflow identifier as with an hyphen, so the issue came only from here. So if I switch this back, I should finally be able to deploy the process. Okay, so here I have a process summary. I don't know if you remember, but when I was showing you the process list, you actually got the same kind of information. And you remember that I was mentioning about the job control options array also. So here you have deployed a CWL application which will take some time to run, right? So there is no way to execute it synchronously. There is no meaning to do so. So you can notice that in the job control option array this time you don't have the sync execute option available, meaning that from a client point of view you are directly aware that you cannot interact with and execute this service synchronously. You only be able to execute them asynchronously, and still you have the dismiss operation which is available, which means that you will be still able to cancel your job execution. You may also notice the mutable parameter which takes the value true this time, which means that you can modify or delete your processes, meaning that you can interact with your deployed process using the OGC API processes part 2 draft specification. So I'm always closing the endpoint to get it, to try to get a user-friendly user interface. So this time what I will do is showing you the details of the deployed process. So here it's basically a process description, because if you remember at the beginning we listed the conformance classes, and within the conformance classes the OGC API processes part 1 code specification defines that you have a conformance class which is process description, which make you able from a client application to know, as the conformance class was listed, that you can get access to the process description. So in the process description you may notice that you have similar information compared to what you get embedded within your CWL file, but this time it's available from a client application. You also can see that the default value from that are coming from the CWL are also available here. And you have the output, obviously. And you have the schema linked with every single object. An input, it can be an input or an output. You have all the details and even much more details in directly within the API description. So once you have deployed your process and you get details of it, what is the next step it is to execute a task which run using these two Sentinel-2 stack items. So what will happen behind the scene when you will execute a process? Server implementation should be generating a job ID, and this job ID will be returned in the response. You can find it both in the location header from the response and also in the JSON object which is returned here. And you can use this job ID to then poll and request information about the running job. So if I try it out and just press the execute button, here I have 201, which means that the server implementation got a job created for your running task, for your running process. And this job gets this newly created identifier that you can find here and there. So what is the next step is to follow the execution of this process on the server side. So how you will do that? You will simply copy the job ID from here and go to the endpoint to access the job status, which is right below. And you simply copy and paste your job ID here. And you get the current progress, which is currently 10. And you have also the message that can be associated with the step. Okay. So here you can see that the execution has been submitted. So meaning that it runs on the Kubernetes cluster. I think there is no meaning to show me for me to show the execution on the Kubernetes cluster.
Not easily from there, no.
Okay. So you wait for the execution to complete.
I have a question.
Yes.
Yeah, please. I don't understand it fully, but this to me looks like a framework where OpenEO backend could be built from. And since these are two ESA projects, like OpenEO as well as some funding from ESA, has there been activities in trying to combine?
Yeah, actually, yeah, I was working. I did work. I made a work in integrating OpenEO UDP, user-defined process, and we have embedded. We have reused the OGC API processes part 2 draft specification, and we are able actually to deploy UDP using this draft specification. But I think actually, having studied both OpenEO and CWL, I have the personal feeling that CWL can go more far than what OpenEO can do. Because in OpenEO, you embed everything in a single box, when in CWL, you can deploy everything anywhere, and you can run it almost everywhere also. Sorry.
I'm just going to complement the answer. Just to put you in context, so OpenEO API is actually a project that is born in the context of the European Commission projects, and ESA has been investing in the backends. That being said, we have recognized that there are lots of similarities, and in a way, we see them two faces of the same coin, because as Gerard said, CWL is more generic, and it was really written to handle with application, like command line application, while OpenEO look more at an audience coming from scientist, someone that actually has a different way to work and wants more an abstract layer, some primitives. That being said, there is currently an activity in OGC testbed 19 called GeoDataCube API that is backed by a standard working group that we just started this year that have the mission to create a DataCube access API that is nothing more than bringing together OpenEO and the application package approach. So in there, you actually see the latest effort in bringing them together, despite it's about DataCube, I suppose. And the current understanding there is that we're going to see this integration in the OGC API process part 3. That is the one that will focus on the workflow element. And so OpenEO graph may become an encoding for a workflow in the same way as a CWL.
So here we have reached 90% of the execution, because at the end of the execution we have a new step that has been integrated lately, which consists in getting back not only the result of the processing, but also the log file of every single pod that has been involved in the execution of the CWL application. So once you have hopefully the OGC API processes is extensible enough to be able to make us able to introduce these links. So traditionally in the OGC API processes part 1 core specific standard, we have only 2 links, which is status location and the result location. Actually, when I say result location, they have a dedicated rel relation type, so you can consult the documentation or the OGC API specification. And we simply added these related links to the different log file. So what can be the next step after you have run and execute a process? It is probably to access the result. So hopefully you have in OGC API processes part 1 core standard, you have a way to access the result. So this is the result endpoint. So you simply copy and paste again the job ID, and you simply press this execute button, and then you will have your S3 bucket. So for a newcomer like me, having a S3 bucket URL like this is of no use. So what did we do is simply having a way to access this. So as it is local to the Zoo project DRU ADES implementation, what we did is simply we provided you a dedicated service process that can be run to access this S3 bucket and read the JSON file that has been generated. So here you have the content of your catalog. So let's say you can kind of browse your catalog. And then if you want to go directly to one item, then you can simply go to the item you've selected. And once you have selected one item, you will have the TIFF file associated with it. Okay, so once you have the TIFF file, what did we? This is a simply demonstration processes. I mean, they are not used in production because we are relying on the workspace API. So here, if you enter your TIFF file, Otsu, it will provide you a link to download the TIFF file. So what you can do then is going back to your notebook, and where it's written URL here, you can simply paste your URL, download your file, and create a copy on your within your notebook, and then show your. Oh, show or not show it. I don't know.
It's worth saying at this point that those last steps that Gerald's showing you there are what you can do. We're not demoing this here, but you can integrate the Zoo execution engine with the user workspace. So when the processing completes and the results are staged out, there is functionality that integrates with the workspace. So it will push the outputs into the S3 as you've shown, but then it will make calls to the user's workspace to call the registration endpoint that Fabian showed us earlier. And so those products are registered into the user's workspace. So in his catalogue, he will see them as discoverable products. And they will also be registered, if applicable, in the data access services as well. And from there, they can be visualized and retrieved, etc. So these steps Gerald's showing you here are sort of effectively manual steps, if you like, just to allow us to see the product of the processing.
It is not working actually. Okay. It is not working and it won't work because, and I know why.
I guess what we can see from the listings there, that the files that were produced, okay, so from the S3 listing that you did, we can see, the stack catalog was produced, the TIFF file was produced, and the stack item that referenced it. So those are the products of your successful processing.
Exactly.
And it's this catalog file that you would pass to the Workspace API, the registration endpoint, and it would then enumerate the catalog and register the items. The reason we're not showing the integrated version of this is because this version of Zoo, DRU, is hot off the press, and we're planning a release, hopefully at the end of this month, our 1.4 release, and the one piece of functionality that we still have to implement is the integration that we had with the previous. So the ADES is the previous effectively version of this. So we've got to re-implement that integration with this new version of Zoo. Okay, so that's it. That's all we've got. If anyone got any questions, burning questions? Otherwise, thank you very much. What I would say is please feel free offline to go and play around with the notebooks if we went too fast. And I appreciate we have gone quite quickly here because we wanted to cover maybe too much. So please feel free to have a play around. And then if you're interested in the project, you can go to our GitHub where there's some information. And also EOEPCA.org is a website. And that will be being revamped very soon as we're going from this first phase that we're now completing. We're going into a new phase. So we will be refreshing that website. So hopefully you can keep an eye on that. Thank you.
So we have a session about CWL and application package in half an hour. I'll be here all week at the TerraDue booth if you want to jump in and discuss CWL or think about your model or whatever. It's also part of the code sprint, OSGeo code sprint. So if you feel that you want to interact with us in that context as well, we'll be there to support anyone with a cool idea to do. Okay.